Recording. Hey guys, welcome back. Welcome to the last video on Logistic Regression series. You've made it this far. I'm so proud of you. But if you're new, then what we've done so far in the series is looked at all the math for Logistic Regression, all the intuition that we needed so that we are geared up for implementing it from scratch. Because in this channel, we like to know the intuition and math before jumping into code so that whenever we code, we understand each and every part of it. Does that make sense? Okay. But if you haven't watched the other videos, that's okay. If you're comfortable with the math already, this should be very easy to follow. Okay, what is logistic regression? Logistic regression is just a statistical method that's used for classification, meaning it predicts one of the two possible outcomes, like yes or no, success or failure, 0 and 1. And where is it used? It's used literally everywhere. In healthcare, to decide whether a patient has a cancer or not. In finance, would it be finance, or I don't know if it would be real estate, but whether a person qualifies for a mortgage or not. Maybe in deciding whether your email is a spam or not. So it's literally used everywhere. And unlike linear regression, which predicts continuous values, logistic regression deals with categorical outcomes, okay? So please go ahead and import these libraries for me if you haven't already. By just looking at the code, I know I never asked you to before this, but please go ahead and import these libraries for me. And then we can okay, no, actually let me explain why we are adding each library so that we're not going into anything blindly. This is just for numerical operations. This is for plotting, visualizing the data that we're going to create, and then for later when we're going to look at decision boundary is going to come up. This one's just for splitting our data into training and testing sets. This one's for creating a synthetic classification data set. This one's for implementing logistic regression for comparison with our custom model. And then this one's just to evaluate the model performance. So please go ahead and import all of this. Now I have a code for sample data. This is what I need you to copy or type out. What is this doing? Let me show you. Okay, so here we're just saying, hey, like I want 500 data points. I want 2 input features because it'll be easier to handle and visualize and all that jazz. And then I'm saying, hey, like both features are useful for our classification. And then I want no redundant features, no duplicated features, binary classification problems are like 0 or 1. And then I'm setting a random state because I want sort of a fixed randomness so that I can reproduce it. Here, what I'm doing is splitting the data into training and testing like this. So what I'm saying is I want 20% of data to be my testing set. That means 80% will be my training set. Same thing for reproducibility. And then I just want it to be fancy and visualize this. You don't have to. But go ahead and please have your data set ready for me. Now we're going to the actual implementation part. So what is sigmoid function? In logistic regression, the sigmoid function, also known as logistic function, is used to map any real value number to a probability between 0 and 1. What does this mean? So when we have our linear equation, we get our z. Our z can be any value, a large value, or a really small value. But what we want in our logistic regression is a probability. We want a number that's between 0 and 1. So what sigmoid function does for us is just take any value of z and give us a number that's always very neatly between 0 and 1, like a probability should be. So yeah, so the logistic regression model starts with the linear function z, but the probabilities must be between 0 and 1. So the sigmoid function ensures this constraint. So if z is very, very large, no matter how large it is, this function just approaches 1. And then if z is small, very, very negative, no matter how small it gets, it can go all the way over here and it'll just approach 0 and never go below 0. So when z is 0, it'll be 0.5. So it's always neatly between 0 and 1, like our probability should be. So let's just define this sigmoid. So we give our z, we don't need anything else, and then I'm just going to return what the formula exactly returns, which is our np.exponential negative z, right? That's all that formula is doing. Okay, that's it. That's our sigmoid function part done. Okay, now for the cross entropy. So what does it do? So computes cross entropy loss, which means how far the predicted probability y hat is from our actual label y, right? So that's all that we're doing here. So quantifies the difference between true class labels and predicted probabilities. Lower values indicate better predictions. Oh, I started and I didn't complete. Okay, let's look at this. And what I want to do here is I want to do something. Do you guys know that log 0 is undefined? And so in our code, we don't really want to have a log 0, okay? It's undefined. Runtime warning, okay. Okay, it's undefined. So what I'm going to do is I'm going to define the epsilon value as this, so that I don't run into a log 0 error, and I'm just going to add it to this and this. Why? Again, just to prevent my log 0 error if any of these accidentally yield 0. That makes sense? I hope that makes sense. Okay, so loss is just going to be np.mean. We're looking at this, and then y times np.log y hat plus epsilon plus 1 minus y times np.log, and then that'll be 1 minus y hat plus epsilon. Okay, I think I need one more bracket, and that should be good. Return my loss. Okay, I have my compute loss. Now computing gradient. Why do I need gradient? I need gradient because I need it in order to update my gradient descent here. So all I'm doing here is getting gradient W, which is how much the weight should be updated, and then gradient B, which is how much bias should be updated. So this is just going to be computing our gradient. So let's compute gradient, and we're going to use it immediately here. So in case you're wondering why, you'll know in 1 second. So that's just, I'm going to take number of samples I have, and then gradient W is going to be 1 by m times np dot x transpose, then that'll be y hat minus y, right? Should be just that. Okay, then what is my gradient B? My gradient B is going to be 1 divided by m, and then my np dot sum. What should it be? Y hat minus y, right? Y hat minus y, 1 divided by m. Yep, that should be it. In case you're wondering, it's my phone vibrating. Yeah, sorry, I should have kept it in silent. Let me do that. Okay, it's in silent. Okay, gradient B. Gradient W I've calculated, gradient B I've calculated. Okay, that should be it for computing gradient. Now gradient descent. What are we doing here in gradient descent? So this one, I'm going to combine a lot of things here, but basically gradient descent is giving us a way to reach the minimum, right? The goal really is to reach the minimum loss, and then our learning rate, which will come up in a bit, is determining how big of steps we are taking towards reaching their loss. And just FYI, we start with some random value W, and then we keep on updating it to reach the next W, depending on the gradient and the learning step. I think I made that unnecessarily confusing, but it's going to come up really nicely here. So I'm going to start training it, and then X. I need Y. I'm going to set our learning rate that we just talked about to 0.1, and then let's say we want to iterate for 1,000, starting as default values. So features would be X shape 1, and then my weights would be NP. I'm going to just say initialize them as 0. So features, and then my bias will be 0. So I'm just initializing my bias, and then I'm having this to store my loss history over each iteration. Okay, make sense? Okay, now let's start our iteration. So for epoch, in range epochs, is that how it's pronounced? I always pronounce it as epochs. Epochs. That sounds weird. Okay, Z is np dot, and then X comma weights, right? Plus bias, and I'm not doing transpose here because it's already in a row column instead of, sorry, row vector instead of a column vector, so I should be good there. I don't need to transpose. And then loss should be compute loss y hat, right? Compute loss y hat, compute loss y hat. Okay, I'm good there. Then I'm going to store it in my loss history. I'm just going to append the loss, and then next thing I'm going to do is get the gradient W and B. That should just be my compute gradient. And then it needs the X, needs the Y, needs the Y hat, right? Okay. And what I'm going to do is widths. Now, this is the update part. This is the part I talked about and made it confusing. This is just learning rate times gradient W. That's all I meant. That's how we update our next, get to our next weight. And then that'll be the same thing, learning rate times the gradient B. That's all I meant, and I just made it confusing for no reason. Okay, widths bias. Widths bias, yes. Okay, I'm going to train our custom model. Okay, so I'm going to say custom weights. Let me do it here actually. Why am I doing it here? Custom weights, custom bias equals to train logistic regression. And then I just need to pass my X training and Y training learning rate. I'm going to set it as the same thing, and then iterations also 1000. Okay. What does it not like? What do you not like? Gradient W. Gradient. Wait, where is it? Oh, in compute gradient. Compute gradient. Did I not spell that correctly? Okay, it likes it now. Okay, now I'm going to make predictions. So predict X weights bias threshold. And threshold I'm just going to do as 0.5. So if it's like 0.5 or greater than 1, predict as 1, else predict as 0. Just keeping things simple, and I think that's a very common threshold anyway, right? So that will be bias, and then again not doing okay, return Y hat is greater than equals to threshold. Okay, this is how I'm doing my prediction, and then I'm going to say my Y predict custom is, should I do it? Let me do it here. Let me predict custom logistic predict width custom logistic regression markdown. Okay, and then I'm going to get one more. Oh no, I'm just going to delete this. Okay, predict. So Y predict custom looks like predict. What does it need? It's my test custom weights, and then custom should be bias. Can I type? Sometimes I just can't type. Oh, yes, you're right. I'm just running that again. Okay, I want to compare it with Scikit-Learn. So, you know, we did all this jazz, and you'll see just how simple it is to use Scikit-Learn. But the important thing is we understand what's happening behind the scenes, right? This is one line of code compared to all lines of code that we did. That's it. But again, it's nice to be able to use that one line of code fully knowing what it is doing, right? So I'm going to do Y train, blah, blah, blah. Okay. And then I am going to do Y prediction. Scikit-Learn would be, again, Scikit-Learn model. Can I type? That's always a question. Dot predict X test. Okay, so we have our prediction with both our custom model and then with Scikit-Learn. So let's look at the accuracy for both. Compare accuracy. And then, okay, comparing accuracy. So I'm going to say accuracy custom is just accuracy. I am still recording, right? Okay, score Y test Y pred custom, right? Y test Y pred custom. Yeah, Okay, and then my accuracy Scikit-Learn will just be accuracy score y test, and then my y print Scikit-Learn. Okay, I'm gonna print these out because it'll be useless if I don't print it. Custom logistic regression accuracy, and then I'm just going to print that out. Accuracy custom. Format it nicely to F, and then that should be it. What did I do? Okay, I think that doesn't quite look right. Accuracy custom, then I have closed this bracket. I wanted percentage. Yeah, that should be fine. Invalid decimal literal. Why do you not like it? You don't like it? Okay. Oh, you don't like the percentage? What do you not like? Invalid decimal literal? Why not? Why not? Okay, never mind. I'm just going to print. Oh, I see what you don't like. Okay, that should be okay. Sorry. And then my Scikit-Learn logistic regression accuracy will be accuracy Scikit-Learn. Okay, print it. Hey, they're pretty close. Okay, that's good. That means we did a good job, right? And printed out the weights as well as bias as well. So looking at the accuracy, it seems pretty similar, but when we look at the weights, they're pretty different, and then even the bias seems to be pretty different. Functionally, they're giving sort of similar accuracy. The reason for having different weights and biases, again, could be because one thing is we just use gradient descent, basic gradient descent, whereas theirs could have used more advanced optimization. And then the other reason might be the differences in learning rate and number of iterations. So maybe our model didn't fully converge, and weights might be smaller than expected, but there might just have used sort of more dynamic adjustment for step sizes for faster conversions. Whatever it is, the accuracy, however, seems pretty similar. And I went ahead and plotted the decision boundary as well, if you want to go ahead and copy this code so that you can visualize. Of course, it's optional, but it'll be just useful for you if you're more a visualization type of person. And the funny thing is where the decision boundary sort of separates, because up to here they seem to be pretty similar, right? And then here where they seem pretty different is where we don't really have data points. So anyway, this is your final video on the logistic regression series. Good luck for more logistic regression fun in the future. We're gonna jump into a new algorithm next week. But if you want me to do a deep dive on any of the logistic regression concepts, please feel free to let me know. But other than that, happy logistic regression and take care.